memory and not as a register.
So if you construct the interference graph, you would remove the ones with, yeah, so you would remove them from this order, right? Yeah. So in this, you will start allocating to EDCB. So if you have already given registers to EDCB, I guess all the registers that are available are over, and hence you cannot give them to
Got it. But
A.
maybe can't we like allocate memory to some other variable which has lesser number of degree, and then maybe allocate A when
Yes.
a register is free?
Yes. So what is the heuristic you want to develop here? Let's say. So what's the insight rather? Why do you want to allocate a register to A rather than a memory to A?
Because A has more number of calls in the program. A is used throughout the program, so more number of calls would be there in the
More number of memory accesses you mean? Yes, right. So that's one thing we always have to decide which variable to spill, right? So we'll talk about it more in fact now. All right. I hope you are enjoying the tool that you have been given, playing with it. Some of you have been asking interesting questions. Like one of you asked, "How is OVR if there is a case where everything has been put into the stack and nothing interferes with anything? Essentially, we constructed the whole stack and the interference graph unnecessarily because anyway we are just going over all the variables and allocating them registers if possible." So that's an observation that one of you had made. Similarly, another of you pointed out that, well, it seems if we just follow the algorithm as it is, we end up spilling a variable that is used many times, which means we would insert lots of memory accesses for that variable. What if we could make a better decision when we decide which variable to spill? We could perhaps spill the variable which is used more. We can perhaps spill the variable which is used less number of times than another one, for example, right? So there are these interesting considerations as some of you are bringing up, which I really wanted you to do as you do this exercise, because, well, the algorithm is known to you, but when you really apply it on different examples, you yourself will think of cases where you can improve, right? I would give you another one that you didn't ask yet, but maybe some of you have thought already. If I decide to spill a variable, right, it will always remain spilled. Isn't it a fine idea to think about unspilling it in favor of some other variable later on, right? Like we allocate a register and we change which variable occupies that register at different points of the program. Can we not do it for spilling as well? Oh, let me give a second chance to a variable that I had decided to spill early on, for example. Right? So these are interesting ideas, and all these ideas have been tried to give interesting variations of a standard register allocation algorithm. Some of them have names. I mean, somebody has actually implemented them in some compiler and said, oh, if I try this particular reasoning for deciding which variable to spill, it performs better in terms of the register pressure on this particular kind of program, and so on. Okay, so there are approaches that use some of the insights that you yourself are coming up with, and that happens, you should notice, once you start looking at more programs, trying to apply it on more programs, see the results. Oh, what happened here, what could have happened, what could I have tried instead of this, and so on. Okay, that's how people develop. So it's good. I'm very happy that you people ask such kinds of questions as I moved around too. And then I want to, before we move ahead to linear scan register allocation and even have some discussion on a few of those bullets, I want to show you some part of this code. You remember this main.java was the one that you basically compiled and passed our test case to in exec.sh. Remember, we were passing our test case to this file main, right? And if you see main.java here, we don't have time to play with it in the course, but you can take this ahead and play with it. That's why I mentioned to you. Here, what do you see? At a high level, you have a node here, which is the node of your abstract syntax tree. You have heard of ASTs in the previous lectures. So given a Java program, a mini Java program here, you have an AST constructed for that program, and this root is essentially the root of that AST. Okay. Then what happens is, we said, oh, there is a CFG gen happening here. So we root dot accept, what it does is it passes root to, let's say, a new file here where I perform generation of control flow graph. Okay. How would you generate a control flow graph? See, I'm telling you these things at high level so that you can play with this code a bit later on. You can explore yourself and find out what's it doing. So how do you generate a control flow graph given an AST, let's say? Think about how would you approach this, not at the code level, but at least assume you have taken as input an AST, and there is a way to go over the AST, do a depth first search or breadth first search over the abstract syntax tree. And now given this AST representation of the program, in order to perform data flow analysis, I need the CFG representation of the program. How would you go about doing it? What logic would you apply? You said you have to flatten it. For what purpose? That also is fine. And let's say you have an AST for a language which was already in 3 address code over here. Our mini Java language itself is in 3 address code, and I have given you the AST for it, let's say. So what could you do? That's what is essentially being done by this CFG gen pass, which is called at line 16 here. So if somebody opens it later, I want you to give some intuition about it. But you are going in the right direction. Why did you want to flatten it? I mean, and you are also talking about 3 address code generation. So what do you want out of the AST if you flatten it, or if you have 3 address code? Why do you intend to do it? So you want basically statements, right? Out of the AST, you basically want to take out statements either in a flattened format or a 3 address code format. Once you have identified the list of statements from your 3 address code, or in this case an AST, now let's say you want to construct the control flow graph. You talked about the leader. Can you expand on it? So I have a list of statements, whether I took it from the AST or whether I was given this list of statements in 3 address code already. Right? That's one thing. Now, once you have the list of statements, what do you do? Mhm. Yes. Oh, let me simplify your task. Let's say each statement is a basic block, or each basic block is just one statement. Right, so many times you don't construct CFG involving basic blocks. See, what's the difference if, let's say, each basic block has just one statement versus I club some of the statements which are linear in control flow into one basic block. What is the difference between the two approaches? Just efficiency. In the first case, you would store an in and an out set with each statement, let's say. In the second one, you would club all of them into a basic block, and with each basic block, you would have an inset and an outset, let us say, and so on, right? But so for simplicity, let's say you don't have a leader here. We just have each statement in a basic block. Okay, every statement, which means it is possible that B1 and B2, there is just one edge over here like this. That's possible. Let's say we give this relaxation for simplicity so that in and out sets can be maintained with each statement. Okay. Now what do you do? So you have each statement is a basic block. Now what do I want to construct the control flow graph? No, no. I may have a loop, for example. Yeah. Mhm. Yes. So how do you know it goes back? Let's say I'm in a while loop and I see the closing brace. Right? I have the opening brace and I have the closing brace. How would I identify from where should I construct the package? Okay, okay. All right, fine. Well, fine. Even if you had just plain 3 address code, if and go to, right, go to L1, I will have to find where is L1. And then I will have to add an edge from that statement to the other statement, right? So even if you had 3 address code, let's say there are no loops, but if the control flow does not fall through, if it's going to a label, let's say, You have to find out which label, where which statement or which basic block is attached to that label, and then you would construct an edge from there to here. Make sense? Right? So that's what somebody did like this. They went over each statement. If it's a straight line flow, then they just connected an edge from the current statement to the next one. If it's a different kind of statement, let's say if it's an if else, then they found the first statement of the then branch, first statement of the else branch, and are correspondingly added the edges. Okay, so that's what is done here at line number 16 and 17, which is straightforward as you saw. It's not too difficult. And then this is what is more interesting. There is a start analysis backward method over here, which is in a class run analysis. Okay, so this is a backward analysis, as you know. Let's look at this piece of code in run analysis.java, and there is a start analysis backward. What does it do? It runs a for loop. Let me zoom in a bit. It runs a for loop here for each class in a list of classes, let's say, and then for each class it gets a list of methods, and then for each method it gets the method name, and then it visits that method's control flow graph in the backward order, right, bottom to up. So this is just wrapper code, let's say, which is making sure that you do the backward analysis for each method of each class. Okay, so the main fun happens inside this visit backward method, as you can see. Now visit backward, can you identify the algorithm which is there inside this visit backward method? Where is liveness analysis happening here? Can you identify its structure? Did you study work lists? Right, you might have studied work lists. So it's actually a faithful implementation of a work list based liveness analysis algorithm, exactly the thing that you have already studied in the course, right? So what we do here is we initialize a work list, we push the start basic block in the work list here, and then while the work list is not empty, we are checking its size is greater than 0. While the work list is not empty, we pop a basic block from the work list, and we mark it visited. We create the previous set of live variables over there, let's say what happened in the previous iteration, and then we apply the transfer function over here, and then we just check if it has changed. Then you would add this basic work list into the basic block, basic block into the work list again, right? So it's the same structure here. Now essentially, where did we go? There is this method handle expression that gets called for each statement from the work list based algorithm, where we are handling different expressions in different manner. Now you won't be able to make sense of this token image and all of this directly, but if you go through this code, you would be able to see that, okay, if I have a plus expression, let's say, and let me tell you that this is the left operand and this is the right operand, I am adding both of them into the result, because in live variable analysis, if you are using two variables on the right hand side, a plus b, then both a and b should be live before this statement. It's a backward analysis, right? So we are adding both the left operand and the right operand in our result, and result should contain the list of live variables. So how do you update the list of live variables after processing each statement and each expression inside each statement is the logic for live variable analysis. If you wanted to do something else, if you wanted to do common sub expression elimination, you would change the direction from backward to forward, and you would just store expressions. Instead of identifying a and b separately and storing them as variables, you can just store a plus b into a list of expressions, let's say, or a set of expressions, right? So I would like you to, at some point of time, may not be today, but whenever you feel you have more into, open up this code and try to modify this implementation to perform some other data flow analysis. This is very straightforward top level implementation, in a sense that it's possible to use the same structure for even other data flow analysis. You can use this framework and play with it. Okay, any questions right now? So find out what does main.java do, go to run.analysis, and in the run.analysis file, we are just defining how do we handle each expression. If you want to implement a new data flow analysis, How do you handle the expression, what parts of the expression to store, in what data structure to store, these things you would change, right? So you can play with this assignments tool, assignments code for even other uh, data flow analysis. That's one thing I wanted to show. If you want to play with it even more, see how can you convert the backward analysis to a forward analysis. You would initialize, instead of the last statement as the start basic block, you would start as with the first statement as the start basic block, for example. So you can play with it and again change this for any other, tweak this for any other data flow analysis. All right. So that's something I wanted to introduce to you before we move ahead. Any other questions in graph coloring based register allocation before we move to linear scan? Okay. So now let's come to linear scan register allocation. And as we said, the motivation is that graph coloring is also quite expensive. So what we could do is, we want to do a one pass over the list of variables, but we also want to take care of liveness, because you know that if two variables are live at the same point, you can't give them the same register. And we would also see a heuristic here, as one of you pointed out, which variables to spill. We would decide it in favor of that variable which would tie up a register for the longest amount of time. Okay, so that's one heuristic over here which was proposed in the original linear scan algorithm. So let us say I have two registers available, one of them is already full, and at the next statement there is a new variable that's there are two variables that's asking for a register. Which one will I give it to? This heuristic says I will give it to that variable which will leave the register soon enough, whose lifetime ends soon enough. Yes, so we will construct all the live ranges like we do previously, right? So you have, in fact, think about it this way. When we talk about dynamic compilation and all later on, I'll tell you that it's the power of static compilation like GCC and others comes from the fact that you have the whole program available. You can see the future very easily, right? Yes.
Rather than seeing who leaves the register soon enough,
Yes.
can't we see who needs the register like most?
Yes. So, well, who needs the register most is the question that you cannot answer easily. But yes, people did try to. Can you tell me why is it not an easy? So, if you see, how do you decide who will need to be accessed the most?
Based on the number of access to.
How do you count the number of accesses of a variable? That's where the challenge starts. Yeah, but you don't know how many times the loop will get executed. Maybe something is in a loop and the loop gets executed twice, and there is something not inside the loop but outside the loop, it's there 4 times in my program. So typically people would do what you said. People would assume that, oh, if something is being used in a loop, let's assume that it will take loop has been written so that you would iterate over it for a longer amount of time, and people do try it out, right? So now let's look at the linear scan register allocation algorithm. The key difference between LSRA and the graph coloring algorithm, which is no longer here, is that instead of live ranges, we would work with something called as live intervals, and it's just a fancy name to mean that we would not talk about a series of start points and end points for each variable's live range. We would talk about the first point at which a variable is live and the last point at which the variable is live. Okay, so instead of multiple ranges, we will just store an interval. What is the interval in the program during which this variable is live? All right, I'll ask you later on when is it okay to do this way. So a live interval for a variable is just a range I comma j such that the variable is not live before instruction j and the variable is not live after before instruction I and not live after instruction j. Just one range or one interval as they call it. Okay, and overlapping intervals imply interference even here, like overlapping live ranges. So what happens is, if I have r registers and n overlapping intervals, what does it mean? R intervals can be allocated to registers and n minus r intervals are spilled. Each interval corresponds to one variable. So this basically means r variables will get registers and n minus r variables will be spilled. to memory, right? Key is choosing the right intervals to spill. So the linear scan algorithm, which was proposed in 1999 in that paper that I mentioned earlier, just does the following. Once you get the live intervals, you sort it in order of increasing start points. Okay. The idea is, whenever you have a free register, at every point of time you check if you have a free register and can you give it to somebody. You can check who needs it by looking at this sorted list. Okay. Whenever something is not live, you don't need to give it a register. If you have a sorted list of intervals, you can figure out, oh, who is active now, who needs a register right now, and if you have a register, you decide to give it to that guy. Okay. Once you give a register to an interval, you maintain a list of active intervals. You say, oh, which of them have been given registers till now. So you again have a list over here, and this list you maintain in order of increasing endpoints. What could be the reasoning? Why would I store the list of active intervals? Active means those variables or those intervals which have been given registers as of now. Why would I maintain this in order of increasing endpoints? Can you guess? What would be the first element of that list? Right, and now I have given it to some. After some point of time, I want to decide, can I give it to somebody else? Mm-hmm. No, as you hit the endpoint, that means that variable doesn't need a register anymore. You remember what was our endpoint? Endpoint is the last point after which the variable is live. So if I maintain the list of active intervals in the order of increasing endpoints, the advantage is I would be able to figure out who can be, or which register can be freed immediately. I would just see the first element of the active list. If its endpoint is over, that means that register, whichever register was given to it, is free now, right? So it's like very quickly find out which interval does not need a register anymore, or basically to find out which register is free now. Okay. At each step we would update active as follows. We would add the next interval from the first sorted list, because that list tells me who needs the register next, and the second sorted list tell me who frees up the register next, right? So at each point I'll add an interval from the sorted list and remove any expired intervals. Expired intervals can be determined from the active list, and the previous list tells me which registers need which intervals need a register now. We have an example, I think that would be clearer, but let's just see what is there here. The restriction is active cannot have more than R elements. If I have R registers, I cannot have more than R active intervals, right? And if active has R elements and new interval doesn't cause any existing intervals to expire, then I have to spill. Basically, if I have no new registers available and somebody is asking for a register, I have to say, I don't have space, I spill you. Okay. And yeah, the heuristic that we would use here is that spill the interval that ends last, furthest from the current position. So when somebody, okay, so there is one confusion here. When somebody comes in, I would give a chance to that interval by spilling the interval that ends the last. Okay. So now what's the intuition behind this? If you ask me for a register, and if I have somebody who is occupying the register for longer than you, I'll throw them out and give you a register. That's the intuition over here, right? The idea is that this will allow you to give registers to more number of intervals. That's where they went with this proposal, right? We would like to give a register to more number of variables or intervals in this case, instead of let one guy occupy the register for a very long time. And why might that be a useful thing to try? Maybe, I mean, that depends on how many times are those variables accessed from that register. So here, think about it once more. At least in this algorithm, we are prioritizing giving registers to more number of variables rather than giving it to some variables that take it for a very long time. If more variables get registers, what happens? Think about that. We are not drawing the interference graph here. It does not require drawing interference graphs. It's a faster algorithm. But if you had an interference graph and you gave registers to more number of variables, what would happen? Well, yeah, but again, how many times you load depends on the number of usages, right? How many times you store depends on that, how many variables you spill. What is the wastage of resource? Huh? Mhm. Yes, so maybe one of the observations from which motivated this could be that, oh, some variables live interval ends late, but many times you don't use them in between. You just create some variable, put some value, and then you return by adding some 10 to it at the end. In between you don't need it. So that could be one intuition behind this. There is one more. Can you think more? Think in terms of the interference graph. If you have given registers to lots of variables in the interference graph, what would happen? The amount of interference would reduce, right? You may be able to give it to more registers if the ones that are given registers are removed from the interference graph. Think of it that way. Okay. So these are some intuitions. Again, how do these intuitions come in? Why do they think? Why would someone think this intuition is good? By observing for many programs. They'll say they develop one intuition and implement it in a compiler, and then keep observing programs in for some time, or let's say take a large number of benchmark programs which are representative of real world programs in that language, and try to see how better is the system, or what's the load on registers. Are we utilizing registers, or are there many points of time where registers are lying free and we have spilled something to the memory? That means maybe we should change the algorithm over here, and so on. And this is how people develop these intuition based algorithms. When you don't have the best possible solution available, how do you develop approximate solutions? It many times comes through experience. Okay, it's a greedy algorithm basically, and in a greedy algorithm, your heuristic may not be good enough for all programs. It may be good enough for some kinds of programs, right? And that's how we have to live over here. So anyway, let's look at an example here. So let's say I have created live intervals for 5 variables, and the start and the end points are like this. So if the live intervals of 2 variables overlap, it means you can't put them in the same register. Do the live intervals of E and A overlap? No, so they can be put in the same register like this. So we have this live interval constructed for each variable now, and now let's start putting them into registers. Let's say we have only 2 registers available. We have maintained a sorted list of variable intervals based on starting point to begin with, right? So based on the starting point, the first variable that needs a register is A. So let me give it a register. When I give a register to an interval, I keep it in a list called as active, and I want to maintain this list in sorted order of endpoints, as we had said, right? At step 2, we get another variable B which requires a register, and I have a register available, so I'll greedily just give to it. I'll not do any further analysis of how and when or others use. I'll just give it, so that it's, again, as we said, this is a linear scan over the number of live intervals. And at point 3, I have a third variable coming in called C. Now I have to decide whether I spill something that is already given a register, or whether I should let C be spilled. So here the heuristic, as we had said, was spill the variable with the longest endpoint, right? C has the longest endpoint here, so I decide to spill C over here. Done. I move ahead. Now at point 4, variable D is asking for a register, but A and B have expired, right? Expiry can be obtained from this active list. A and B's endpoints are already before this, so A and B have expired, which means I can give D a register, and at point E, similarly, I can give E a register, and notice how cleverly we have sorted them in the order of increasing endpoints. So E will expire first, I'll be able to quickly remove it from here. So if somebody asks for another register at this point of time, I would be able to quickly see that, oh, E's interval has expired, and hence I can give that guy a register. Okay. Here, if C's lifetime was only this, what would I have done? C would have been given the register as per this heuristic, and in order to give C a register, what would I have spilled? B, right? So that's linear scan register allocation. It's a very simple algorithm, as we said. You need to sort some lists and so on, which means there is some cost in initially, but once you have those lists for a program, you can just keep going over one statement by other and then decide which registers to allot at what point of time. So 2 registers for this example and 1 spill. Is this an example for which graph coloring would have done anything better? Well, first of all, graph coloring, let's say this variable C was not live for the entire duration. So graph coloring would have split the life ranges. Maybe it's here and somewhere. So if live ranges could be split like this, maybe graph coloring would have avoided that spill if it found that C was not live at the point where A and B both were live together. Because let's say at this point this live range ended and then here C was not live, so it could have brought it back from spilled memory after this point of time and then continued. But then we have just stored a linear list, a single list for each variable, single interval for each variable. All of you with me? Yes. After D ends. Okay. So in the default algorithm, no. You make a decision only when someone requests for a register, but you could have. That's a good tweak to this, right? That, oh, instead of making a decision when someone asks you to make a decision, just do it eagerly whenever somebody expires. That's a good fair point as well. You could have made a decision whenever somebody's endpoint comes in, or you could have made a decision after each statement, let's say, but that might be too slow. Again, might not be useful.
Would we perform penalty be compensated for the loading and unloading the?
That's again something we don't know. How many times would it be loaded and stored in future is some. So see, it would be extremely interesting. Many compilers allow you to perform profile guided optimizations. Okay, it would be very interesting to, if for a certain program you care about the register allocation that comes in, it would be interesting to profile the program, find how many times each variable is, let's say, really loaded from the memory, and use the profile to feed this information to the register allocator and decide which variable to spill. Right? Run the program once, let's say, get the profiles, feed the profile back, and modify the algorithm to decide which variable to prioritize while giving registers based on the profile.
But profile may contain only one type of input.
Very good. Profile may contain only one type of input. How do you, so all these lead to, interesting research topics. How do you make sure that the profile run is representative of real world? How do you generate test cases? Software testing comes in over here. How do you generate test cases that you think will help you make a better decision over here? Right? So there are, all these areas are connected. Compilers with performance analysis, with software analysis, software engineering, all these are pretty much connected areas. Somebody was asking me outside during lunch break that, do people use artificial intelligence and machine learning in compilers? Let me tell you, AI and ML have been used in compilers from a time when these terms even didn't exist. What was the original full form of AI? Not Air India, not artificial intelligence. Can you tell what was it? Before AI, artificial intelligence came in, there was another famous full form of AI in computer science. Abstract interpretation. Okay, abstract interpretation is the like data flow analysis are a way of performing program analysis. Abstract interpretation is a way of defining program analysis. Okay, abstract interpretation tells, when I normally interpret a program, I would execute it on the hardware. So I would execute it as per the semantics of the machine. if I interpret it abstractly in some other machine where I am not working with actual values but with symbols, let us say, what would I do? So liveness analysis can be described as an abstract interpretation pass where I say, oh, when I see A equals B plus C, what do I update in my state? Instead of actually performing B plus C and storing it into A, I might be doing something else. I might be storing B and C into one data structure and removing A from another data structure, right? So the art of doing all this is called abstract interpretation. That was AI's first full form. Then of course artificial intelligence became more popular later on, but and then yeah, Air India nowadays uses AI, but fine. So now coming back to the topic, AI was used in determining many of these heuristics from a long time ago. Maybe in early 90s there were lots of papers that used to use AI for this. Okay, so it's not really uncommon to use AI in compilers, but there are reasons it's not really possible to use AI in many other parts of a compiler. Can you name a few? Can you use AI to just generate assembly code and for any language and trust it? There is no guarantee that your semantics are preserved. You cannot risk using AI and then saying that, oh, I got this assembly code, let me run it in the nuclear center. Exactly, that's the reason. So you cannot guarantee, if it is 99.99% correct, not okay, because you want semantics to be as it is when you translate from one form to another. But there are other problems for which people use artificial intelligence, like how to decide which registers to allocate if I cannot give it to all of them. Right? Run program thousands of times, get lots of data, don't worry about it, and then feed it and so on. So things that do not require correctness are where people have been using AI in compilers for longer than even I was born. But it's not really possible to use it for all cases because you need, or at least in cases where you need correctness, which happens to be every now and then for compilers. Anyway, coming back here, so this was an example of how people developed a faster register allocation algorithm. I'll just add a few comments here. It's significantly faster in practice than graph coloring. Many of you were struggling with constructing liveness information and so on. This also will need liveness information. So when I say fast, it doesn't save you from computing liveness information. But when you make decisions about who to allocate variables to, you're just going over the live intervals in one order. Right? And it's still not as good because holes in live ranges are not taken into account. As we said, a variable may be live not from here to here in entirety, but at some different places, and there may be holes in its range which won't work over here. And in graph coloring, on the other hand, you could have maintained different graphs at different points, and some variables would not interfere, would not be shown as interfering with another variable if at that point they are not live, because your liveness analysis results there can be used at each point based on the inset, as we did in the afternoon. And another thing is, a variable once spilled, if it remains spilled forever, there are algorithms to give a second chance to a variable, as one of you suggested. If I have spilled something, I can decide to bring it back on my own, thinking that, oh, now I have more registers available, why do I keep it spilled? Can I bring it back? Right? And many compilers that require efficiency of compilation would use linear scan, even though many compilers also use graph coloring based register allocation that prioritize register utilization over speed of compilation. They may try to use graph coloring based register allocation. So both of these are very popular, and there is one more semi-popular, I would say, register allocation algorithm which was proposed, and it was shown to be very effective for embedded devices, again, devices where you have very few registers available, for example. And coincidentally, on many of these devices, when you write your C programs, you would perform lots of bitwise operations. Okay, and when you do that, one thing you can think of is, can we pack more than one values in one register? So in both the algorithms that we have seen till now, we give one register to one variable, but maybe some variables require less amount of space to store than a complete register. I have a variable of an enum type, let's say, that can take only 4 kinds of values. So I need only 2 bits to store that enum, but a register is 64 bits, let us say. So I can actually pack more variables inside a register if my architecture allows me to address different parts of a register with different instructions. For example, a set of low bits and a set of high bits. So I can try to allocate 2 variables into the same register and so on. So this is done on systems. These kinds of improvements are proposed for systems where you have the scarcity of resources is much more pronounced than others. Modern CPUs have lots of registers, so we don't usually worry about it. Any questions? Okay, so now before we end, I want to utilize today's time to build up some background on Java, because tomorrow we would look at many memory optimizations. Memory optimizations are more interesting in the context of object-oriented languages, and that's where we need to know at least about one of them, at least an idea of the cost associated with one of these OO languages, and we would see Java for it. So how many of you have used at least one OO programming language? Forget Java, C++, raise your hand. Object-oriented language. Oh, almost all of you. Something. If not C++, Java, which one? Python has classes and so on, right? So most of you write programs in object-oriented languages, right? And what things distinguish object-oriented languages from others? What are some special properties about OO languages? What is the most important, interesting thing in OO languages than others? Huh? The object-oriented. What is an object? One of you maybe. Yeah, many of you know, I know. Yeah. Instance of a class. And what does a class include? Variable. Properties. You are a JavaScript programmer. You are a Python programmer. So a Python or a JavaScript programmer would likely use the word properties. A C++ or Java person would use the word fields. And as one of you said, you can also call them variables. They are essentially variables, right? Yeah. So there are variables or fields inside a class, or properties inside a class, or attributes inside a class, which are like variables. And there are functions. If those functions are virtual, you typically call them methods in OO parlance. Okay. So now you have these fields and methods, and I just want to show you, so this would be slightly off topic. It's anyway 5:05. It's a slightly off topic discussion for 15-20 minutes. It's not, today's discussion is not related to compilers, but it will help you understand tomorrow's discussion very well. Today's discussion for the next few minutes will be more like showing how does Java work in some sense. Okay. And of course, by the end you should realize why is it interesting to learn about it. Yeah, we have it here. No, wait. Yeah. Yeah, so I have a class here. Can you see this much? This font is fine. So I have a class here where there is a lot of commented code. Basically, I have a class animal that has 2 fields x and y, 2 properties x and y, 2 variables x and y, 2 attributes x and y, whatever you want to call them. And there are 2 methods here, sound and tail. What is this method called? Constructor. When is a constructor called? When you initialize, when you create the object, right? So you create the object, and what is typically the purpose of calling a constructor? Right, to basically initialize the fields. What should be the initial values of the fields, so that you, in the instance that you create, you know some values are initialized over there, right, of the fields. And then there are methods here. I have a class monkey that extends animal. Okay, what do we mean by extends? Inheritance. All of you know about the word inheritance, right? So when I inherit, what happens? Correct. So all these are common across all OO languages. Okay, don't assume that I am just teaching Java here, but in general I am introducing some OO concepts here because memory optimizations are particularly interesting for OO languages, as we would see tomorrow. So I have y and z, which means the properties of animal would come into monkey, and then there are two more properties y and z over here, right? And then there is another constructor. Note that this call is inserted by the Java compiler whether you write this or not. This line 37 is inserted by the Java compiler. Can you guess what does it do? Calls the parent classes constructor, right? So a call to the parent class constructor is by default the first thing that happens in a constructor, and then you may have other code as well. In Java, there is a parent class for every class. So monkey's parent class is animal, but what is the parent class of animal? You don't see it, but there is. There is an object class in Java, java.lang.object. Java.lang is the package. Java.lang.object is the parent class of all those classes that don't have a parent class explicitly defined using extents. Okay, all of you with me till now? And then there are methods. Now there is a method sound in animal and a method tail in animal. There is another method tail in animal over here. So what do we mean? If I have a child class with a method whose signature is the same as another method in the parent class, what do I say here? Is there a keyword associated with this? I override that method. So you can say that monkey overrides the method tail from animal. Okay, till now all of you are with me. So now let's say I do this. Animal A is equal to new animal, and system.out.println is like cout and then a backslash n at the end. That's what is, forget about what is system, what is out, what is println. It's just a method call in some class called system, a field called out, and in that fields class there is a method called as println. Okay, so let's not worry about this part. I am printing a.x here, plus is concatenation in Java, then I put a space here and plus a.y, and I am calling a.sound over here. What would get printed if the code compiles and then I run it? What would get printed on the screen? 10, 10, 10, 20. Oh, okay, animal sound 10, that's from line 5, and from line 4, 10, 10, right? So that's what we expect. So what I'm doing here is I'm compiling this class, this Java file. When I compile, okay, maybe I can show you first. So here I just have object semantics.java. How many classes are there in this file? 3. Object semantics, animal and monkey. Okay, I have 3 files here. Now when I do java c object semantics.java, I get animal.class, monkey.class and object semantics.class. Tomorrow we will open these class files and see what lies inside them. But for each class in a Java file, you would have a new class file generated which has Java bytecode. Okay. And now, so when I compile and then if the compilation is successful, I am running it by supplying the name of the main class. What is the main class? Why? It's the starting point. It has a main method defined. Okay, if a main method like that is defined, it's the starting point of your program. So I need to tell which class has the main class here. What the JVM will do here, it will try to find a method named main in object semantics. If it finds it, it will call it. This will be done internally. Okay. So if I run this, as expected, I get 10, 10 as the output from line 4 and animal sound 10 as the output from line 5. Now let's make things more interesting. Let's comment these two out. First, tell me whether this line is valid. Will it throw a compile error or will it be fine? It will throw error. If you say it's fine, tell me if. So animal A is equal to new animal was fine. Monkey M is equal to new monkey should be fine, right? Right? This should be fine, no problem. And let's see whether this is fine. Yes, no compilation error. It's fine. Okay. Why is it fine? Those of you who thought it was an error, can somebody tell why? For them, can somebody tell why is it fine? The pointer type is animal. The variable type is animal and the object type is monkey. So in Java or in typically most O languages, a reference variable of a certain class is allowed to point to objects of that class as well as its children's classes, is descendants classes. Okay, since monkey extends animal, animal pointer can point to a monkey object, and that should tell you whether this will work. monkey M is equal to new animal. Should this be allowed? No, and it's not. As you can see, it says incompatible types, animal cannot be converted to monkey. Okay, because you might have studied this word called as is a relationship. So when I say monkey extends class, what I mean is monkey is a animal. It does not mean animal is a monkey. Okay, and hence an animal pointer can point to a monkey object because monkey is also an animal, but a monkey object, monkey variable cannot point to an animal object because an animal can be a dog as well, a cat as well. Every monkey may not be a cat, or no monkey is a dog or a cat. So you need not be able to point to every animal object through a monkey pointer. Okay, does that make sense? Which monkeys are there in Chennai? I know them very well. What's the variety of the monkey here? The species of the monkey, not variety. Bonnet macaques, right? What's the one in many other parts of the country in the north? Rhesus macaque. Okay, so you may extend monkey by two more classes. Rhesus macaque extends monkey and bonnet macaque extends monkey. You know why is it bonnet macaque? Next time you see a monkey in IITM campus or anywhere around here, please make sure you realize why is it called a bonnet. Their hair are parted in the middle like this, and they look as if somebody has put a bonnet on top of their head. Its color is very different from the remaining head. It's like somebody put a wig on their head and so on. That's why they are called bonnet macaques. Okay, rhesus I don't know. Anyway, notice their head next time you see them before running away. Okay, so animal cannot be converted to monkey. So that's something you realize now. Monkey is an animal, but animal need not be a monkey. Okay. Now let's make it more interesting. What should be the output here? B dot x and B dot y. So let's see what did we do. In animal we initialized x and y to 10, and in monkey we initialized x, y and z to 20. Yeah, so is there an x in monkey here? No, which means which x am I initializing to 20 here? The parent's x. But is there a y in monkey? Yes, so when I say y equals 20, have I updated animal's y or monkey's y? Half of you say animal's y, half of you say monkey's y. So based on that, the output here would also be interesting. So b dot x, is there an x in monkey? No, there is only one x which is in animal. So what will you get here? 20. And b dot y, that's the confusion, 10 or 20. Let's see, 20 and 10. I will not tell you why is it the case immediately. I'll uncomment the next line. And I have now inserted typecasts here. So you saw b dot y printed 10 there, right? Let's keep it uncommented. B dot y printed 10 here, B dot x printed 20 as expected, and B dot x will still print 20 over here. And now what should this print? B dot y again, but with a typecast to monkey. And what would that mean if it prints 20 as expected? Previously, when you said b dot y, you got a 10 out of it, and when you said monkey b dot y, you got a 20. You learned two things from there. First, you have both y's available in a monkey object. You have your parent's y as well as your own y available, right? So how many fields will be there in a monkey object now? Can you tell? 4. Which ones? Animal's x, animal's y, monkey's y, and monkey's z. There are 4 fields present in a monkey object. When you define another field with one of your parent, you don't override your parent's fields. That's how you understand the meaning of the word override. We'll go to methods soon. When you you just shadow the field. Okay, when you shadow it, it also exists. And the proof is that you are able to print its value. When you say b dot y, you got the parent field's value, which was 10. But when you did monkey b dot y, you are telling the compiler, give me that y which is of type monkey. Give me access to that y which was a field declared in the monkey class, and hence you got a 20 out of there. Similarly, if you say monkey b dot z, it gives you this guy. What if you did? Let's comment this. What if I did? So now, in order to understand the second part, first I told you what you learn is that, oh, parent fields are also there, they are not killed. Okay. Second, let's try to print here. To understand what's the second thing you learn here, let's try to print b dot z. Now what do you expect? Why so? That's the right answer. You're right, but for a single word. The object is of type monkey. The variable is of type animal. Okay, make sure you understand the difference. What you create using new is the object, and what you have on the left hand side is a variable or a pointer. In Java, pointers don't have star, but every reference variable is a pointer in Java. You say here that pointer b is pointing to a monkey object over here. Okay, so now what's the type of b here? Animal. And does animal have a field named z? No, and that's why you get a compile time error over here. So let's compile it. It says, very helpful error, cannot find symbol. Which symbol? Variable z, where in variable b of type animal. In animal it can't find a variable z. That's what it says, very clear. Reading errors is extremely useful, and that's why this worked. If I typecasted monkey b to monkey, then it said, oh, look at monkey now, don't look at animal, don't look at the type of the variable here. We are telling the compiler, look at monkey, just look at monkey. Is there a b here? Is there a z in monkey? Yes, and hence this did not give a compile time error. Okay, this works as we had expected. So this is the first part. Well, that was the first part, and the second part is, which you learned just now here. I'll spell it out. Fields are bound statically in Java. Okay. What do you mean by the word static now here? Fields are bound statically or at compile time in Java. The compiler can figure out which field are you referring to. The compiler is allowed to figure out which field are you referring to. And here the compiler looks at the static type of the variable to figure out which type are you referring to, unless you have put a typecast here to tell it that no, forget about the static type, assume it's a monkey type variable and then look for the field z. Okay, does that make sense? So write down in your notes, fields are bound statically in Java, which means you would look at the static type if it's there. And then we'll finish with talking about methods. Okay, now let's look at lines 11 and 12. Animal b equals new monkey, is it allowed? Yes, an animal pointer can point to a monkey object, right? B dot tail at line 12. I have a tail method in animal which prints animal's tail. I have a tail method in monkey which prints monkey's tail. When I say b dot tail here, what should get printed now? How many of you say animal's tail? How many of you say monkey's tail? And now let me make a statement. You don't need to learn a language if you know its semantics at the top level. Let me speak out one sentence and you would be able to tell what's the right answer. Fields are bound statically in Java, but methods are bound dynamically. Now what should be the output? Monkey's tail. And why? Because the type of the object pointed to by B is monkey, right? B is pointing to an object of type monkey over here. And why do I use the word statically and dynamically here? Why am I using this guy to call it statically and this guy to call it dynamically? This is created during runtime, that's one thing. In fact, you may not know what is it pointing to at runtime. What if I have an if condition here, some condition that depends on user input, so I don't know what will that condition resolve to, no constant propagation can help there. If some condition b is equals new monkey, else b is equals new animal. And then after the if else I have b dot tail. So the compiler can't even figure out whether b will be pointing to a monkey object or animal object at this point of time, which means you have to find which tail method is called only at runtime. At runtime, well, one of those branches would be taken and b will be pointing to either an monkey object or an animal object, and hence the runtime will take a decision on which tail method to call over here. So the decision to bind methods is made dynamically, whereas the decision to bind fields is made statically. That's what is meant by fields are bound statically and methods are bound dynamically. In JavaScript, for those of you know it, fields are also bound dynamically. What does that mean? If you were working with JavaScript, you can expect b.y to print monkeys y instead of animals y. So find out any language where fields are also bound dynamically and try to find out what's the output printed there, right? For a language where fields are bound dynamically, the compiler will not be able to figure out which field is bound even during compile time, and that decision is also postponed to the runtime. Okay. So now, okay, since you said that, let me just show you that when I did b dot, and now probably you would understand the meaning of the word override and never forget in your lifetime. Just look at this example. If I do animal b dot tail now, see, b dot tail printed monkey's tail. Animal b dot tail, what should it print? Monkey's tail or animal's tail? See, for fields, what happened? When I typecasted it, it basically just looked into that guy's field. But what will happen here? Yeah. Is there anybody who thinks it would print animal's tail? I have given enough hints that you won't say yes. But I hope you see the reason why it won't print animal's tail. So now if I just compile and run it, as you can see, that also prints monkey's tail. So what's happening here? What is the meaning of the word override? You kill the previous thing. So there is no way for a monkey object, if the monkey class has overridden the tail method of an animal, there is no way for you to call an animal method which was overridden using a monkey object. The object is of type monkey. So only monkey's tail is what you will obtain here by calling the tail method. The animal's tail method is gone. It's not accessible anymore from a monkey object, whether it's referred to by a monkey pointer or an animal pointer or whatever pointer over here. Does that make sense? And well, finally, if I have b dot sound, what would happen now? Yeah, because you have not overridden the method in the monkey, so then you get animal sound printed over here. Okay. So this is what I wanted to tell you. Now, okay, why is this? Well, first, fine, you learned some fun stuff here. You learned how OO programs work and what is meant by static and dynamics. All this is also relevant, but it's also relevant in terms of the optimizations that we would see tomorrow. So when I have a monkey object, I have my parents' fields as well as my fields over there. What if I had another pointer to some other object? Let's say there was a dog pointer stored in monkey for some reason. If there is a field of a dog object, how will I access it? I'll take the monkey pointer first, then I'll access that field, then I'll go to the animal, the dog object, and then access its fields, right? So object-oriented languages, even though they provide such a nice real-world abstraction, you can model the real world by denoting it in terms of classes and creating instances of classes where objects talk to each other by passing messages to each other through method calls and so on. In a language that allows all this level of abstraction, you also have a lot of cost associated with it. You have a lot of cost associated at compile time as well as at runtime. You perform indirections in memory. What if I access frequently a monkey type object in a program, and then from a monkey type object a dog object in that same program? What if I keep doing this indirection again and again and again? Could I have done something such that this indirection can be accessed faster, for example? Could I have optimized this memory access? If I have a method call like this, so here we said, oh, the compiler cannot determine which tail method is called, you have to postpone it to the runtime. But if you just look at this program, can you not tell which method tail will be called? Right? We said something like this: if some condition and then b is equal to new animal, else b is equal to new monkey, and so on. If this is there and then I have b dot tail, well, I won't be able to figure out which tail method is called. It could be either animal's tail or monkey's tail. But if this was the code, couldn't I have done something better? I could have made the decision about which method tail is called here at compile time itself, because I know in this program that B is only pointing to object, and in between B is not reinitialized, B is not a global variable. You could have figured out what is B pointing to at this point and optimize that method call as well. You could have directly linked it with a monkey method, for example, monkey tail method, for example, instead of postponing the decision to runtime. Right? So all these are interesting optimizations that can be performed related to memory accesses. In fact, if two objects are being accessed close enough, you can make sure they are allocated in the same region of the memory so that they can be loaded into the cache in the same cache block and so on. So all these optimizations also come into picture as you talk about OO programs more frequently. Okay. So this is what we would start tomorrow. We have seen how do you allocate registers. The level next to the register was the cache memory and then the main memory. We'll talk about all these cache and memory optimizations tomorrow. Some of them at least. Okay. Any questions? Okay. So then see you tomorrow at 9 a.m. We are finishing almost on time, 5:30. Thank you.